Give me 1 second. Yeah.
All right. Okay. Okay. Please go ahead. Yeah. We have
Okay.
John Müller.
Yeah. Thanks everyone for being here. And yeah, I'm Johannes Müller. I'm a PhD student in Leipzig at the MPI for Mathematics and the Sciences, and this is joint work, sort of a little bit of a follow-up work into a little bit of a different direction with Marius. You just heard talk. Yeah, and obviously, I mean, this has received fundings from different things, so here they are. So what we were trying to do here is, I mean, Marius talked a lot about deep Ritz methods, and I mean, the role of boundary penalty versus exact boundary values and resolution and error decay in this scenario. And this is basically complementing the study in a different ansatz of PDE or numerical analysis for PDEs with neural networks, which is residual minimization. And I will start by giving you a very quick overview over my talk, and basically what a lot, not all, but some very popular current approaches to the numerical solution of PDEs with neural networks boil down to is the Ritz method, which was proposed like a while ago. This is 1909, so over 100 years ago, where Ritz basically said, if you have some energy functional over a function class and you want to minimize that, what you can do is you just, take a parametric function class that lives in that space and you minimize it like over those parameters. And this is actually a very nice paper. He does it sometimes by hand back then for polynomials. And I mean, we have seen in Marius' talk already that one thing that is not quite clear is sometimes how to deal with neural network ansatz classes are boundary values. And there are sort of two directions one can go into, and one is to design ansatz classes with exact boundary values, and the other one is to, take maybe up front the easy road and to just allow arbitrary functions and penalize boundary terms, boundary penalty. So introduce a boundary penalty. And what Marius has talked about is the case of the deep Ritz method. So basically, we write down the variational formulation of a PDE and then minimize that variational energy. And then, we basically had two regimes here. So if we have an ansatz class that satisfies the boundary values exactly, then, it's pretty standard theory, I would say, to see, like for coercive functional, that the convergence rate will more or less be the approximation rate. Assuming perfect training here. And if we consider the deep Ritz method, but with not exact boundary values, but with a boundary penalty term, then, our results boil down to that we can guarantee that the convergence rate is at most 2/3 of the approximation rate. So I'm introducing this boundary penalty term decreases our rate of convergence of the method, or at least, it's not clear how sharp this is, but depending on the function class, I'm rather certain that it could also be dropping in fact. And what I'm trying to argue here today is how the situation looks like for residual minimization that I will introduce in a second. No worries if you don't know it. But sort of the takeaway that should really be, that everyone should take away from this talk is the following. If we do residual minimization with exact boundary values, then we will see that the H2 convergence rate is basically the H2 approximation rate of this ansatz class. And if we go away from exact boundary values, and use boundary penalties, at least the common ones, then we can only guarantee H1/2 convergence, and the H1/2 convergence rate matches the H2 approximation rate. So here we don't get a drop in the rate, but rather a drop in the sort of norm in which we measure the convergence if we switch from exact boundary values to boundary penalties. All right. So I will start by presenting the setup for people that don't know residual minimization, which I mean I guess is a rather popular approach to a lot of problems. But I mean, we study the prototypical elliptic PDE, which is this following Dirichlet problem. And I mean, we just make the ansatz that we want to solve it within parametric function class. And the other approach, or I mean, there are different, more than two, but I mean, another approach to deep Brits is to not write down the variational formulation of this problem, rather to minimize this residual energy, which basically, I mean, measures the deviation of this equation to be satisfied. I mean, this is very common, I guess. I mean, and yeah, I mean, it's done in a lot of applications, not only for PDEs. And this dates at least back to the 90s, this approach with neural networks, and was recently revived, I would say, by some people. They sometimes call it deep Galerkin method. So if you heard that term, those are, depending on how you set things up, more or less the same. And here I want to mention one thing that's a little bit different to the case of the deep Brits method. In the deep Brits method, I mean, we have this penalty parameter also, if we use a boundary penalty at least. And then this boundary penalty term, or this choice of the strength of this penalty, is really crucial because it basically changes the variational problem you're solving. And here the situation is a little bit different in the sense that no matter how we choose our penalty, I mean, it must be a positive parameter, but then, I mean, like the unique minimizer over the function space of this energy will always be the unique solution to our problem. So just it's a little bit different here, but yeah, I mean, one thing is, okay, like this slide, I mean, this works for any parametric function class, and we don't have to put a lot of effort into designing our function class. The other road to go into is to design function classes with exact boundary values. And this, so I mean, it's the idea to design a function class here. This is like all H2 functions that restrict to G, lowercase g on the boundary of omega. And this approach also dates back to the 90s at least. And one way to go is that we design sort of a cutoff function that is 0 on the boundary and non-zero at the interior. And the second function, which is a lift of the boundary conditions. So, I mean, this is just an H2 function that restricts to G. And then if we have any parametric function family, we can define this associated family by first multiplying the function with L, so cutting it off at the boundary, and then adding our lift G. And this will be an H2 family, and I mean, under my conditions, and have exact boundary values. This is a very nice approach. It can be very difficult to do in complex domains, and a lot of engineering has been going into this. I mean, there are different papers doing it, and sometimes actually people propose to learn or express those functions again by neural networks. Maybe one thing like that sort of started in our interest in this question, or in the question of theoretical things we can say about these two approaches of exact boundary values versus analyzed boundary values in residual minimization was also, I mean, there are several studies, empirical studies, but one very explicit one is this following by Chen et al. And here they train, both like for the deep Brits method and the deep Galerkin method, or residual minimization, with and without boundary penalty. And sort of the takeaway is that, like in both cases, here the terms without boundary penalty decay very quickly and don't have plateaus or slower decay. And therefore, they hypothesis, they conjecture that exact boundary values help the training process and also lead to more accurate solutions. And so we wanted to see, like, what we can say theoretically. So those are, I would say, the takeaway of a lot of empirical studies. So I said there are more than only the one by Chen, but this is makes it very explicit, I would say, this comparison. And one is increased accuracy and a faster training process. And I mean, we will more focus on the increased accuracy because we will not study the training process in this thing. But I mean, again, as Marius mentioned, I mean, this is a really important thing also to do. Because, I mean, training neural networks, as we all know, is not a trivial task. And maybe just to further remarks before we get into our results, one can do similar constructions that construct exact Neumann boundary values or Robin boundary values. And second remark, as I think also Marius mentioned it before, I mean, those function classes can be, I mean, sometimes one can design them, let's say, but one thing that I'm not aware of, at least, are good approximation theoretic results of neural network ansatz classes that satisfy boundary values exactly. And I mean, one can make certain assumptions and qualitative assumptions of density sometimes, but I don't know a good, or at least they're not sufficiently studied, I would say. All right, let's jump into our theoretical analysis of some of the rates, how things decay. And I mean, just here to present our setting again. So we consider the Dirichlet problem for now. I mean, it can be extended to other problems. And theta will denote the parameter space of a neural network ansatz class. And we assume that we have H2 regular functions. I mean, otherwise we cannot really write down our residual energy. And we fix some positive penalty parameter. And this is the loss we're talking about. So we have first the residual of the PDE, and then also a residual of the boundary values. And the first thing we could observe is the following. If we have this setting, and if we have some domain with, let's say, smooth boundary, then we get this estimate, which bounds the HS error of a neural network approximation of the true solution UF by the loss function, or loss square root of the loss. That this holds if and only if S is at most 1/2. And I mean, this estimate was established for S up to 1/2 before, but this sharpness was not really proven before, or not written down. And to give you an idea how this proof works, is at the core, it really relies on this one estimate from Schechter from the 60s that allows us to estimate the HS norm of a function U by the means of the HS minus 2 norm of the Laplace of U and some boundary terms measured in HS minus 1/2. And then if we apply this for S equal to 1/2, then we almost immediately get this upper bound. Because, I mean, in this loss function, we have the L2 norm of the Laplacian, basically, or Laplacian of this difference. And then the L2 norm on the boundary. And here, for S equals 1/2, this is like a negative Sobolev space, but we can also upper bound this by the L2 norm of the Laplacian. And this has been essentially realized before by people by Shin et al. But the other, like this strictness is a little bit more delicate, but this estimate already gives you a hint, because, I mean, if we assume this would hold, then we would be able to control this norm. And here we have a boundary term of something which has strictly positive Sobolev exponent. We would be able to control this by something where the boundary penalty only, or boundary term only, appears in the L2 sense, and you can come up with a contradiction. But this basically tells us if we penalize boundary values and we are successful in minimizing our residual energy, we can only guarantee that our found neural network function is close to the true solution in an h1/2 sense and not better. All right. Maybe a few remarks on how we can obtain stronger statements in this boundary penalty framework. The first thing is if one uses a stronger penalty on the boundary values, for example, the h3/2 norm instead of the L2 norm on the boundary values, then we can actually, with this approach, get H2 estimates, or if we penalize something in between L2 and H3/2, then we will get something in between. But I guess, the H3/2 norm on the boundary of the domain is not as easy to implement as the L2 norm. So I guess, it's not that commonly used approach, but I'm not claiming it wouldn't work. And the other approach that one can go is basically by interpolation. So if we want to bound the HS norm, obviously we have this interpolation inequality, and we can bound it by the h1/2 norm and h2 norm with some exponents. And if we now combine this with our estimates of the h2 norm, we end up with the following thing. So we can upper bound the HS norm of the neural network function to the true solution of the PDE by two terms. The first term, here this is just interpolation. And then this first term we can upper bound by our theorem before. The second term we can just upper bound by the triangle inequality. And the H2 norm of the true solution will be, that will just be some constant. The H2 norm of the neural networks that we get from the training process is something that one would need explicit control over, which is not a priori clear, because this is not directly controlled by the loss we're minimizing. And then we have the second term, which is the loss function. So, if we can prove like H2 boundedness of some sort of outputs of a training process, then this will also give us an estimate with respect to a stronger norm. But the exponent that we can estimate it in decays if we make S larger. All right. So if there are any questions in between, you can also interrupt me. But I guess people are maybe not in the chat, but still, if you see any questions in the live stream, you can also interrupt me directly. All right, let me now contrast the setting to the case of exact boundary values. And again, we consider this prototypical elliptic PDE, the Dirichlet problem. And here we also assume for now that our problem is H2 regular. I guess it's pretty common knowledge that there are very mild assumptions on which the Dirichlet problem actually is H2 regular. But we didn't want to elaborate on those too much. So what this means is that we can estimate the H2 norm of the problem or of the function with exact boundary values by up to a constant by the Laplacian of a function in the L2. Furthermore, now we make the assumption that our network functions u theta, they're again in H2, but they restrict to our boundary values that we want to have. Therefore, the loss function we're minimizing now only consists of this one term, and we don't have a penalty term because, that's just 0. And, the contrasting theorem that we get here is that under these assumptions, the distance of neural network function to the true solution of the PDE can be estimated in the H2 norm up to a constant, which is precisely the regularity constant, times the square root of the loss. And for certain domains, like convex domains, one can estimate also, I mean, this regularity constant quite explicitly, which is nice. Yeah, so I mean, I don't have a remark here. So I'm just going to remark it verbally. So I mean, this is quite in contrast to the case of analyzed boundary values, where we could only establish this estimate for exponents up to 1/2. So here in this setting, if we I mean, assume that we are able to make this quantity small, this residual small, and we're guaranteed to be H2 close to our true solution and not only H1/2 close. All right, the proof is as simple as it can get, I guess. I mean, just writing down the H2 regularity in this case on the subspace of exact of functions with exact boundary values already directly gives us our estimate if you set it up correctly. And then, I mean, what we can also do is now express our or decompose our error of this method into an optimization term and an approximation term, which looks quite similar to the things that Marius has talked about in the case of the deep roots method. And in this case, we get this explicit estimate where we found can H2 upper bound the H2 norm, H2 distance of the neural network function and the true solution by this term, which resembles an optimization error with very explicit constants. And also here, an approximation term that we can upper bound by the H2 approximation error of our parametric class or neural network class. And this here tells us if we, I mean, up to successful-ish training, which is not a trivial statement or assumption, H2 approximation implies H2 convergence, which is in quite a stark contrast to the case of boundary penalty, where H2 approximation only yields H1/2 convergence. All right, this proof is if you set, or if you use this SEA lemma that Marius has shown you, again, relatively simple, and it boils down to this fact that one can realize that on the subspace of H2 functions that have exact boundary values, the energy norm we get from, I mean, the residual energy is up to constant, so it's equivalent to the H2 norm, and therefore we can just apply the SEA lemma, which lets us control the H2 distance by terms of, of this energy distance and an approximation error. So once this is set up correctly, this proof is relatively simple. And yes, I mean, I made this remark before. This was the one I was looking for. So this theorem shows that H2 approximation with exact boundary values implies H2 convergence, in contrast to the boundary penalty case. Okay, so far so good. Obviously, this phenomenon and this results and line of arguments is not tied to the Dirichlet problem or like the Laplace as an operator, but one can make this work for general elliptic PDEs. So, I mean, this is, I guess, your pretty standard diff-Agrad setup for an elliptic PDE, which I will not elaborate here in full detail, I guess, because, I mean, everything goes through with the exact same line of reasoning, but maybe at certain stages we have to think a little bit more. But it's completely analogous that we can estimate the H2 norm up to the regularity constant of the problem and the square of the energy. All right. Another extension from this kind of arguments that I can make is the case where we measure the residual in other things than only the square of the L2. And for this, we can allow arbitrary exponents that we measure it in and arbitrary Sobolev exponents. I mean, those are like Lebesgue exponents, P, order of the Lebesgue of the Sobolev spaces. I mean, one needs a little bit of different assumptions on the boundary. I mean, boundary regularity, I guess, is pretty common and pretty well known to most people. And obviously, I mean, the right-hand side, the data needs to be more regular for those arguments to work. And then also our neural networks need to be more regular. But then if we, modify this loss to, measure the residual in a higher order term and with a different exponent P, then we directly end up with this generalization, which lets us bound the WK+2 norm just by the regularity constant associated to this Sobolev spaces and this elliptic PDE and the pth square root of the loss. And again, this tells us that if we are successful in minimizing this loss, we get a certified WK+2 closeness of our solutions. And maybe I should have remarked this earlier, but this equality is relatively nice in the sense that it can be used as a posteriori certificate in the sense that once we come up with a parameter theta, this is something we can just explicitly evaluate via numerical integration. And then, okay, this quantity, depending on the setting you're in, you can also bound this explicitly as I have shown you before. So this a posteriori gives you a method of just like for any parameter, like after or maybe at the end of the training process, certifying how close you are to the true solution. Okay. Now I want to very quickly touch on parabolic equations without spending too much time on it, and then I will wrap up and we will have time for questions or comments or criticism. And yes, so in the parabolic world, the setup obviously looks a little bit different. So we have time-dependent problem here. It's a heat equation that can also be generalized to other parabolic equations up to certain assumptions. And yes, so we solve it on the time cylinder interval times in domain. I didn't introduce I guess. Have some boundary terms on the spatial boundary terms and temporal boundary terms, initial boundary terms in time. And we make the following assumption that we have a neural network class of functions that lives in this space. It's a little bit intimidating maybe, but just like, H1 regularity in time with respect to L2 in space, but also L2 in time with respect to H2 in space, and exact boundary values in space. So we assume that this is satisfied exactly, and also our initial boundary values should be satisfied exactly. And I've showed you before that like a common approach of like how to design such function classes. And then our residual loss looks a little bit different because we have now something over to time space cylinder, quite similar. And then the theorem takes the following form, that we can upper bound this norm of our neural network function to a true solution in this norm of the space X, which is, I'm just going to jump back, this space, and we just use this sum of the two norms of the associated spaces if we're intersecting. Can upper bound this by up to a constant square root of the loss. And I mean, this basically follows from maximal parabolic regularity theory, which tells us that this operator, I mean, the heat operator in this case, so time derivatives minus Laplacian, from the space X into the space where our right-hand side F lives in, is a linear homomorphism. And then we, I mean, get this also relatively easily, where C is just the operator norm of the inverse of the solution operator. Okay, so now let me wrap up. I mean, I'm just repeating two of my items from my first slide because I think that's really like the conceptual takeaway that everyone should have from this talk. For Deep-Ritz method, we've shown you before that with exact boundary values, the convergence rate is equal to the approximation rate, where with boundary penalty, the convergence rate can drop up to, but no more than 2/3 of the approximation rate. And here in the case of residual minimization, we have argued that, I mean, just by regularity of those problems, with exact boundary values, the H2 convergence rate is equal to the H2 approximation rate with exact boundary values. If we don't have a function class with exact boundary values, but rather penalized boundary values, the norm, like the modulus basically of convergence, will drop from H2 to H1/2, and also showed that this is not just an artifact of the proof, it's actually a sharp thing. So we cannot do better here. I mean, there are several very interesting follow-up things one can do. First one is, and I mean, people have worked quite hard on this, but I think this is still not completely settled. It's the question how to construct good function classes with exact boundary values. And also, what are the corresponding approximation guarantees for such function classes? This is something that I think has received relatively little attention. And obviously, I mean, the sort of big elephant in the room is the triending dynamics. So how can we ensure that training is successful? Because I think in those kind of problems, one is a little bit in a different setting than in most of supervised learning, where things tend to be really highly over-parameterized. And I think here things, and also maybe proof strategies, need to be adjusted a little bit to study this. With that, let me conclude, and thank you for your attention. And yes, here are some of the references. Perfect.